we've come to the end of the course, and let's see what we have done. All right. So this was a slide that we had put up in the beginning of the course. That EE210 is going to be, this is how the structure of the course would look like. We'll look at the device models, and we looked at the BJT model only. MOS model, we ran out of time. Amplifier building blocks. And then we said that we'll take the different building blocks that are there and integrate them and make an operational amplifier. So in one slide, what is EE210? How about this one? In one slide, what are the kind of things that you have done? We have single transistor amplifiers, the basic stages, the common emitter, the common base, the common collector. And then we have pairs of transistors which have interesting properties, which we've looked at: Darlington pair, cascode connection, when the collector of one transistor where the signal is applied, it's connected to the emitter of the other one, the cascode connection. The active load, where the PNP serves as the load of the NPN if you apply the signal here, or if you apply the signal here, then the NPN serves as the load of the PNP. All right, so the cascode here, the active load here, the differential pair that you see here, the class B push-pull stage here, current mirror, pairs of transistors which are very useful. And there are others also. This is not an exhaustive list. There are others that we may have done and it's not listed here. And then taking the basic stages that you see here, taking maybe elements from here and integrating them and making a more complex circuit with better properties. This was one example where we didn't use any active load, a combination of differential pairs, common collector, common emitter circuits. This one is more interesting. You can see this part here, which is not given over here. So this is a transistor pair. That's interesting. NPN, PNP transistor pair. And we had active loads here, current mirrors being used as a load, transistor being used as a load. And we had a class AB, this kind of a circuit at the output here. All right, so these are, as you can see here, we have taken a few of these elements, combined them together in this particular form. There are many other ways in which you can combine, and you can get many interesting results. For example, let's take cascode. What can I do with cascode? So let's pick this one here. So this cascode, we saw, I'm not drawing the full schematic here, only the small signal one. So cascode, if I apply a signal here and I take an output here, and we saw the advantages of the cascode, that it allows you to get high gain without sacrificing the frequency response. The Miller's effect is minimized in this particular configuration. So that's a cascode with a resistive load. Now, one of the ways of generating new solutions is to combine various existing solutions that are there, solutions to different problems here. So I can take this cascode, and if I want to build really high gain, then I know that I should take this resistance out and substitute it by an active load, right? So I could do that. This is my sort of drive transistor, cascode, this thing here, and the active load is used over here. All right, so I can get this particular amplifier configuration. So this will give us higher gain, much higher gain compared to this one, and I won't suffer that much in terms of frequency degradation because Miller's effect is minimized here. Now I could think of taking the load here and making the load into a cascode load. So cascode with active load, and I could think of doing this. Note that everything above this plane here, this V0 here, all this is load. And everything below here is your drive transistor here. Okay, so this is a cascode connection that we are using. And earlier we had used a resistive, then we used the active, and then we've used a load. If you look at the load here, the emitter of this transistor is connected to the collector of this one. Emitter and collector are connected together, which is the same as emitter and collector are connected together. So this is a cascode connection here again. Cascode connection here. And why are we using it? Well, if you look, we have been saying that the net gain at this particular point depends on the Norton's current and the Norton's resistance. Norton's resistance is resistance looking down and in parallel with resistance looking up. So in this case, if you look down, you see one transistor and another transistor, resistance looking down is very high. If you look up, then you see only the resistance of a PNP stage here. So the gain of this particular point, Norton's resistance, would be decided by this one here. So now when we add another transistor, then what happens is resistance looking up also becomes very high. And resistance looking down is also very high. So you'll end up building very, very high gain. You'll end up building very, very high gain here. And so you could use that configuration here. But remember, one of the problems that occurs here is that, okay, one end is, you may have a negative supply or ground. The upper end is VCC. And when you stack all these transistors one on top of each other, then what happens is you have to maintain each transistor in active mode. And therefore, the amount of, you have to maintain this transistor in active mode, this one also in active mode, this one and all that. So what happens is the swing at this particular point starts getting limited. Okay. So what are the alternatives? As I said, one can take these elements and play around with it. Okay. So another one that you can think of. So this one, we call it as cascode with cascode load. This is a cascode and the load is also a cascode. So here's another amplifier. And we have the tools with us right now that we can take this, we can predict what the gain is, what the frequency response is, what the input resistance is. We can predict of each one of them. We have the tools, we can easily calculate what the gain of this particular stage is going to be. Using the method that we talked about, break it up and reuse the results, 4 or 5 results that we had said. Based on that, you can calculate what is the net gain at this particular point here. Look at the other one. Suppose I have a problem with this one. Okay. These were more or less straightforward. Taking a resistor, replacing it by an active load, or taking this one and replacing it by a cascode. The second one is more innovative. It tries to build a cascode where you don't suffer from this problem here. Problem of stacking one transistor on top of each other here. It at least tries to minimize it. So what it says is the following. It says, note that for cascode, all that you're looking for is this drive transistor should not see a high load here. Should not see a high load. Why? Because at this point is where there is collector-based capacitance which is getting multiplied by Miller's effect here. So at this point, it should see a low resistance. That's the aim of the cascode. Low resistance here. And the place where you're building the gain, that's where you should create high resistance. High output resistance here. Alright. So if we can do that, not just with a NPN. So what we can do is, there's another strategy where what we do is, we draw a line here, let's say, and whatever is on top, we fold it down. We fold it down. And as we fold it down, what we do is, if you see an NPN transistor, make it PNP. And if you see a PNP transistor, make it an NPN. So let's see. Look at this configuration. Can you see that what we did was, we took this and folded it down. Folded it down, so this transistor became PNP. And this resistance became the same resistance. Resistance remained the same. But then, what I need to do is, I need to bias both of them. I need a current here going and current here going. So we add a resistor here which will be connected to the supply. So that would supply the current which is going into both of them. And we take the output here. So we call this configuration folded cascode. It's actually a cascode. Why is it a cascode? Collector of this is connected to the emitter of this one. It's a cascode connection. Except that it's not two NPN transistors. It's a NPN and a PNP. It's a very, very popular configuration because now note that I have not stacked one on top of each other. This is here and this is here. Alright, so that's the folded cascode. Now, once you invent a new configuration folded cascode, now you can say, well, I can take the resistive load and make it. What can I do with the resistive load here? I can make it active load. So I can make an active load here. All right. So you can play around with this. Once you have a folded cascode configuration, then you can put an active load. You can have a resistive load. You can put an active load, and you can do more things. Okay. I could take one more transistor and put it down here as well. Okay. So you can do all of that. And note that at any point, what I can also do is I could take this transistor out and then replace it by a Darlington to build a high input resistance here. So I can do that also. I can take it here and put it over here. All right. So one of the ways of generating new amplifiers with new characteristics is to take the existing elements that are there and combine them, connect and combine them, and then you will generate new stages with new properties. Let's take the current mirror here. Right. The current mirror was, we said, whatever current happens here, the two transistors are matched, the same current flows over here. Well, and if you think about it, current mirror, what we are looking for is that when I see from here, this stage acts like a current source. It acts like a good current source. So I can take this one here. So this is what we call as a simple current mirror. I can take this and I can make a, what will I call this? Look at this connection. We'll call it cascode current mirror. We'll call it cascode current mirror. Now, why am I building a cascode current mirror? Well, if you look from here, if you look down, what do you see? Only R0. When you look down from here, you see R0 multiplied by 1 plus whatever of this. So the resistance here becomes very high. So it's a cascode current mirror, will give you very high output resistance here. It's a very good current source with very high output resistance as compared to here. So I can take this simple current mirror and make it cascode current mirror. Well, remember this differential pair? Differential pair with current mirror load. What can I do now? I can take this simple differential pair with current mirror load. I can do this. Differential pair with cascode current mirror. Right? Differential pair with cascode current mirror. I can build this. And now, what else can we do? If we have cascode, then we have folded cascode. So I can do a differential pair with folded cascode. Differential pair with folded cascode load. So now see, once we have built these elements here, there's a lot that we can do with it. By connecting, combining, and all that, we saw examples here. There are many interesting things that we can do based on these elements. We can make a comparator, and all kinds of interesting things are possible now with these particular elements. So, any questions at this point? Otherwise, what I have is this course has been a journey for you, a new journey, and for me, I've been visiting this for many times. And when you go on a journey, what you do is you click photos so that you can relive the memories, right? So I have a collection of photos. So if you want, I can go over those photos here. Maybe you can recollect, right? Here is a snapshot that you may have seen in the beginning of the course. This is where we started. Remember our journey? Transistor needs to be biased in active region to amplify. A very important point. If it's not biased in active region. But did we see exception to this? A transistor needs to be biased to amplify. Did we see exception? A place where we didn't bias it? We didn't bias the transistor. The signal itself, turned the transistor on and worked. Class B stage. All right. So, in general, it's very hard to make any statement which is universally true. So if I say every time you have to bias a transistor in order to make it useful, well, in that case, we didn't bias the transistor. The signal itself was strong enough. So when the signal came, it turned the transistor on and, drove the load here. So anyway, a transistor needs to be biased in active region to amplify. All right. Analysis. But two parts of analysis. So the moment you have biasing, then you have two kinds of signals. I mean, two kinds of voltages, a bias voltage, and then you have on top of that signal. And therefore, the analysis is also broken in two parts here. Bias point analysis and small signal AC analysis here, right? So you substitute DC model, you substitute small signal AC model in order to carry out the analysis. This was also, if you recall, an important part here which tells you the whole of analog design cycle. How does it start and where does simulation fit in? What is the role? We use very, very simple models, 0.7 volts, and a transistor itself is fairly complex. We neglect lots of things. So we use simple models to design, and we know that the design is not going to be very accurate, and so we go ahead and simulate. Simulation is such an important part of the design cycle. We simulate, and then we go ahead and tune the design. We saw that in the op-amp as well. We made our op-amp, and the biasing was not right. We went back to the simulator, and we tuned the design to make the biasing a little bit correct here, okay? So simulation is very, very important part here to check your design, to tune your design. And this is where we use accurate and complex model, and this is where we use simple models. So the role of simple model, the role of complex model, the role of simulation, all of that in a simple diagram here. The model of the transistor, by now, you know this by heart, your DC model. Very, very often what happens is we keep on using 0.7 volt model and we forget this. That ultimately the transistor's collector current is related exponentially with base emitter voltage, VB by VT. There are places where you can use 0.7 and there are places where you can't use 0.7. Okay, so where you have to go back to this expression here, that collector current is exponentially related to VB by VT here. So that's something that we should not forget that. That's the basis here. And the same thing of model of a transistor of BJT in forward active mode. Then the other thing is characteristics of amplifiers are frequency dependent. It's just a collection of slides taken from the course here. Okay. These are the capacitors, external and the internal. And we had this figure here. Low frequency behavior is caused by all the external capacitances. Midband, this is the main frequency band that is of interest to us. And these are all the internal transistor capacitances that matter. And appropriate model has to be used. So in this entire region, we have the simple model here. And in this region, we have our high frequency model here. Then our main amplifier here. Simple common emitter amplifier with this gain, input, output resistances, with the trade-offs that are there in the common emitter amplifier between gain, input resistance, gain and output resistance, input and output resistance here, and the importance of beta. Where does beta come? Very often when asked why is beta important, people say, well, the gain depends on beta. If I don't have enough beta, I won't get enough gain. But look at that. The gain is ICQ RC by VT. All you need to do is two transistors, we saw that two transistors with very different betas can give you the same gain. All you have to do is make their ICQs the same. Okay. Where gain beta enters into picture is in the RF, which is directly proportional to beta here. All right. So these are the trade-offs. That's very important. Looking at a configuration, not simply from an analysis point of view, but looking at it from the design point of view. Being aware of these are some fundamental trade-offs which are not there in common emitter, but are there in other amplifiers also. The trade-offs between gain, input, and output resistance here. The swing part. One part, of course, we saw, we always have to make sure that our transistors stay in active mode. And that gives us, you know, a limit, a consideration on how large a swing I can get. The other thing that we have to bother about is our transistor is nonlinear and therefore it has distortion in it. And so there's a swing which comes about from the distortion point of view. And this is also, you know, we keep on saying small signal, right? So how small should you use? This is what tells you. VBE, the amount of base emitter voltage that you apply, divided by VT multiplied by 25, gives you the second harmonic distortion. So how small should I apply? It all depends on how small a distortion are you looking at. If you want an amplifier to be very linear with very little distortion, then your small signal VBE should be much smaller than VT. All right, so this is what it's telling you. How small should this voltage be? The other thing is, very often we forget, we keep hearing small signal, and we tend to think that everything has to be small signal. In the sense, every voltage has to be small signal. Note that small signal only means the base emitter voltage is smaller than VT. It does not say that the voltage here at this node has to be small. The voltage at this particular node can be a volt, 1 volt sinusoid, 2 volt sinusoid. That's not where the issue of small signal comes in. Small signal comes in only at the base emitter part. Okay, voltages here can be very large. This is another one which I find that there is a bit of confusion. The swing is limited by two terms here. One is saturation, the other one is distortion. And so when asked to calculate what is the maximum voltage swing, so let's say these numbers are given, RB, RC and all that, and when asked to calculate what is the maximum voltage swing that this amplifier is capable of, then what you need to do is evaluate the first term, evaluate the second term, whichever one is smaller, you do that. The second part is, this is designed for maximum voltage swing. If I wanted the highest possible swing from here, how do I design it? And that says that you should design it by taking VCEQ in this particular form. Okay, so that's design. Now you can't use, when asked, for example, how much is the maximum voltage swing, and you're given RC, RE, all of that, you can't just say VOM equal to VCC by this expression here. You can't apply that expression. That expression would apply only if the amplifier has been designed to give this kind of a swing, where VCEQ has been chosen to be of this magnitude. An amplifier may not have been designed like that. May not have been designed like that. So you have to go back and here. You have to, once the design is given to you, then you go ahead and use this one here. If it's asked to you, design an amplifier with the maximum possible swing with a certain kind of HD2, then you go ahead and design it like this. You say, well, I'll have to choose VCQ of this magnitude and therefore other things as well. Okay? So realize where this particular expression is valid here. And we also saw this is something which is very commonly there, that bias the transistor in the middle. VCQ should be equal to VCC by 2. And we saw that this is not really true. You can't really bias in the middle. It all depends on how much harmonic distortion you're willing to tolerate. This was one of the things that you find in analog circuits. Small things make a huge difference. And here is a common emitter amplifier. And, you are facing a lot of problem with distortion. Distortion is really limiting your swing. And a very small resistance. If you recall, go back to your notes and see that very small resistance, 13 ohms, 10 ohms and all that. That's all. It helps in making the amplifier very linear. Drastically reduces distortion. Okay. So small amounts of resistance introduced in the emitter, we discussed this in detail, with negative feedback is able to reduce distortion and brings a lot of other benefits. Brings benefits of higher input resistance. You can apply larger input voltage here. And also we have not discussed here, if you calculate the frequency response, the bandwidth improves of this particular amplifier. So negative feedback introduced here brings a lot of benefits. At the expense of, it's always, whenever you introduce negative feedback, you're exchanging a set of good qualities, set of good things that happen against something else that you sacrifice. Usually is the gain. You end up sacrificing the gain. So one of the strategies is, if you want a good amplifier, what you do is you build up enough gain. First of all, build up enough gain, and you don't have other things which are very nice. Build up enough gain. Let's say you're looking for a amplifier with a gain of 100, right? But with nice properties, other things, bandwidth and all that. So what you do is, you don't build an amplifier with a gain of 100. Build an amplifier with a gain of 1000. Multi-stage amplifier, build a gain of 1000. Then what do? 1000, you apply negative feedback and sacrifice gain by a factor of 10. Okay, so initial gain is 1000, you sacrifice the gain, bring it back to 100, and what do you get? you get all the other benefits that are there. Input resistance may go up, and depending on how you apply the negative feedback, you can reap the other benefits, bandwidth and other things that are there. So that's a strategy. That's the strategy behind an op-amp. Nobody is really wanting a amplifier with a gain of 10 to the power 5. Right? There are very few applications where you would say, I need a gain of 10 to the power 5. The whole idea behind an op-amp is build a very high gain amplifier, 10 to the power 5. And then what do? You've seen that all the most of the time op-amps are using negative feedback. So you take your 10 to the power 5 gain, apply negative feedback, reduce the gain, and then you get other things. All the other benefits that come through the application of negative feedback. So this is an example here. A very small resistor here connected brings a lot of benefits here. And as I was saying, that this is not really valid for a stage like this when you don't put. But remember why this is not valid. VCEQ, VCC by 2 equal to V ohm is not valid because the transistor is highly nonlinear. And then you have to take the nonlinearity into account, and this is a better expression. But if you use a resistor here and you're able to reduce the distortion to a significant value, the distortion no longer becomes a very important limiting factor. And then this thing goes back and may make sense here, that you bias it in the middle. VCQ is VCC by 2. Because the only reason, remember, if I take distortion here, let's say distortion becomes negligible. Distortion becomes negligible, this will go up to VCC by 2. All right? All right, so after looking at all of that, our common emitter amplifier, if you look at the common emitter amplifier, you realize the importance of biasing point. If you look at input resistors, you look at gain, you look at swing, and I've not put, you look at bandwidth, and you look at all of that, everything depends on here. ICQ, VCEQ. And therefore it brings, makes it important that if everything in my amplifier is determining where I bias it, then the stability of the bias point is very important. If my bias point starts drifting due to temperature, due to beta, due to whatever else is there, then I have a problem. All my amplifier characteristics would drift. And therefore, if everything depends on this, I need to make my bias point stable. And this circuit bias point was very sensitive to changes in beta. And so we arrived at, remember all of this? We said, well, this is a very stable bias point, much stable bias point. If you use a dual supply here, it doesn't depend much on beta. But if you need a single supply one, then we arrived at a circuit like this. That a single supply design, which is insensitive to beta, was this one. And of course, just by structure, it doesn't become insensitive. You'll have to choose, you have to design it properly. You have to choose emitter resistance, which is much, much larger than RB by beta. How much larger and all that details are given here, depending on how much variation in IC and all that you can tolerate. So that helps you decide what value of RE and RB we choose. Lower cutoff frequency. Our methods are, again, I think we did only with common emitter amplifier, but the method is very general. All that we need to do is we use a short circuit time constant approach, take one capacitor at a time, short the other ones, find out all the frequencies that are there. Whichever one is the largest, and if it's significantly larger than the other one, decides the lower cutoff frequency. Okay, so the method is applicable to all lower cutoff frequency calculations. Upper cutoff frequency calculation. One of the methods was, well, transform it into your high frequency equivalent circuit. The methods is one of open circuit time constant now. So take one capacitor at a time, open circuit the other one. Open circuit the other one, find the equivalent resistance, find the time constant, sum of the time constants, and you get the value of upper cutoff frequency here. And in this context, we said the C mu can be simplified, can be brought to the left and the right of you can break the feedback between input and output using Miller's theorem and makes the calculation simpler for upper cutoff frequency. A more general, which is not just applicable to common emitter and this kind is this one here. Whenever I take my BJT amplifier, what will I end up with? A more general circuit, some resistor here in RC, something in RE here, and something connected in the base here. So this is a more general high frequency equivalent circuit that you'll end up with. And you have to calculate two time constants, one due to C pi, another due C mu. And these are the general values of resistance here. R pi is of this kind, R mu is of this kind here. And so this is a very general calculation of upper cutoff frequency for most of the circuits here. Each transistor will have C pi, C mu of this kind of a configuration. And for each transistor then, you could predict, for each C pi and C mu, you can calculate using these two expressions. If you have multiple transistors in the circuit, then for each transistor C pi and C mu, you could apply this and get it. Okay. In general, when you are, let's say you have a multi-transistor circuit. If you have a multi-transistor circuit and you have to calculate what is the upper cutoff frequency. Okay. In general, what you do is, note that what we are doing is finding time constants. So in your circuit, you go and look at, there would be some nodes. So what you need to do is break your circuit into a set of nodes. There would be some nodes which will be high impedance nodes, where you know that the Norton's resistance is very high. Those are high impedance nodes. And some nodes where you're looking into the emitter and all that are low impedance nodes. So upper cutoff frequency is decided by those high impedance nodes. So if you have a very complicated circuit, break it up, look at all the nodes. Usually you'll find there is one node where the impedance, one or two nodes where the impedance is the highest. At all other places, the impedance is lower. In a circuit, you usually find that. And the upper cutoff frequency is decided by that particular node, the highest impedance node. So what you do is, you zoom down to that particular node, find out what is the net resistance at that particular node, and what is the net capacitance at that node. And upper cutoff frequency is simply F equal to 1 over 2 pi, the net resistance multiplied by the net capacitance. As a first estimate. As a first estimate of what the upper cutoff frequency is. Alright. And of course, if you want a more detail, we know that this method, where did this method fail? Do you recall where this method failed? We predicted FH equal to 2 pi, R pi, C pi, R mu, C mu, and it failed. It failed very badly. Huh? Common collector. In common collector, this particular method, we calculated R pi, C pi, R pi, C mu, all of that. And we calculated, it was giving us a bandwidth of maybe 100 megahertz or 200 megahertz or so. And when we go ahead and simulate, we find bandwidth in gigahertz. Bandwidth in gigahertz, because all of these are, as I said, the simplified ones are based on one should not forget the origin of it is based on the dominant pole. One single pole, which is, its frequency is dominant as compared to other poles and zeros that are there in my system. And in common collector, it so happened that the dominant pole was cancelled by a zero. And the non-dominant pole then became the key factor. And the upper cutoff frequency was much higher. So remember, all these things that we do, all the analysis that we are doing, are all simplified analysis. That's why the role of simulation is so important. That after you do the analysis, simulate it, and the simulator is not making any such assumption, one pole or two poles or whatever. Simulate it and check. And check that your design, your analysis, and all that is correct here. So the role of that is extremely important here. This is the part where we said, most of the time we spend analyzing. As you can see that we have so much material in any course is loaded with material, so we spend time analyzing. We don't get time to put it together. Take the different elements of the course, put it together, and connect and combine and create something. Or look at the connections between the different elements here. So this is very, very important. All right. So the connections between, for example, the gain input and output resistance that we already saw, the connections, the trade-offs that exist. In circuits, these are some of the most important things. What are the trade-offs? How can I exchange gain with input resistance here? This was, how can I exchange gain with input resistance? Well, this was, you can exchange gain and input resistance, as you can see here, through ICQ. If you increase ICQ, you increase gain and you compromise RL. That's the route for exchanging, for causing a trade-off between gain and input resistance. This is a different way of exchanging gain and input resistance here, where you leave a part of emitter resistance unbypassed. So what you do is you decrease the gain and you build up input resistance. So that's another way of causing an exchange, causing a trade-off between the two. So gain input resistance trade-off was important. Gain swing trade-off. Different ways in which you can do that. This is the part, this is an interesting part here. When I leave a part of emitter resistance unbypassed, note that what happens is the gain goes down, the swing goes up. 18.2, 110. Swing here is only 0.39. The swing here is 2 volt. Gain swing trade-off. You're making amplifier much more linear, and therefore you can get much higher swing. But you compromise on the gain part here. Gain bandwidth trade-off, of course, is a very popular trade-off, which you hear at all places here. There is a trade-off between gain and lower cutoff frequency. If the capacitance is limited, in the sense that you can't use capacitance above a certain value. If there's no limit on how large a capacitor you can use, then there is no trade-off between the gain and lower cutoff frequency. But most of the time, there's an upper limit of how large a capacitor you can use. Maybe 100 microfarad, 10 microfarad. So there's a limit. There's exchange here. And the upper cutoff frequency and gain, there's an exchange here which is clearly visible, at least through this particular part here. There are other places through which the exchanges occur, but this part is clearly visible here. All right, design. So that was design perspective, and now you come to actual design. All right, being aware of all the trade-offs that exist in my design, the actual the design of this common emitter amplifier, and we said that almost all the parameters depend on ICQ, VCEQ, all of this here. So instead of looking at all these parameters, a better way of looking at design is in terms of these parameters here. You have to decide in your design, you have to decide on ICQ, VCQ, the bias point. And we said another thing, which is the emitter voltage here, VE. And then, of course, RC, CE, and design would also involve selecting a proper transistor, proper beta, proper, and the values of the capacitances and all that, depending on the high frequency response here. And in this context, this was a important picture here. That supply voltage in this case is limited, and you have to allocate. You have to allocate supply voltage. Part of it you may allocate to gain and swing. Gain here depends on this part here. This part here depends on the swing. And this part here decides the stability of the bias point. All right. So in most cases, you will find that, in a design that there is a resource which is precious, and there are multiple demands on that particular precious resource, and you have to allocate, you have to budget. All right. So this is showing the supply voltage in this case is a precious resource. There are multiple demands on the supply voltage here, and how do you allocate? Allocation of this one here. All right. And in this context, as I said, very often what you'll find is, you don't want to cope with this complexity. And so people develop rules of thumb. And one of the rules of thumb in literature, in books and all that you'll find, well, don't go through that. Make this 1/3, 1/3, 1/3. All right. But that's arbitrary, right? It shows you how you divide, how you allocate. So if somebody tells you, your family budget or whatever, make 1/3, 1/3, 1/3. You look at the demands and then you decide how much time to allocate, how much money to allocate here. So that's arbitrary, saying that 1/3 I'll allocate here, 1/3 I'll allocate here, 1/3 I'll allocate here, no matter what the situation. Okay? You don't do that. So this is telling you how you allocate, depending on gain, depending on swing, depending on the stability. That's how you allocate how much drop should take place, how much drop should take place, how much drop should take place. All right. This was a picture that we said, okay, that was that once you take an amplifier, once you take one particular solution, and then you look at the problems. I mean, if this particular little stage could solve all our problems, then we should have ended the course right there. That's it. I have one amplifier stage which does everything, and let's close it. So that had problems. Lots of problems. And out of those problems came, possible solution approaches here that you can see here. Active load, differential pairs. So let me ask, what was the differential pair a solution of? That we cannot take this amplifier and build it on chip because the capacitors cannot be built here. So that came out of a solution to that particular problem here. What about this one here? Oh, let's say the active load. What about the active load? Very important configuration. What is that a solution to? High gain, but that's not complete. High gain with low supply voltage. I don't require a high supply voltage anymore. All right, so that's the solution to that. Otherwise, I can build high gain. If you give me 100 volts, I can build high gain. Right? But then this says with 3 volts, you can build very high gain. All right, so that's the solution here. What about common collector? What is that a solution to? Low output resistance, high input resistance, but even this can give you. Right? We said, we can exchange. This can give you low input resistance, high input resistance, low output resistance. Even here, right? I can make a transistor, make an amplifier with high input resistance. I can get 100K here also. But remember what we said? That this stage is, no matter how much you do. Remember we took a case here, we said, okay, you can make a transistor common emitter amplifier with a gain of 1. You can get high input resistance and you can get low output resistance. But the capability of this amplifier is far superior to this. Factor of 10 or 20 times better in terms of giving you high input resistance and low output resistance here. So it's several times better than this. Okay. If it were only a little bit better in terms of input and output resistance, we wouldn't have had a special stage here. What about this one? Common base came out of Miller's effect, but we didn't succeed, right? We didn't succeed in this. So this was interesting because, you look at it and you say, well, maybe what if I do this? And we came up with the idea of common base, but it didn't succeed. It didn't give us a high gain, high bandwidth. Remember, it gave us a high bandwidth only when we drove it with large resistance. And with large resistance, then it doesn't give you any gain. And then actually what it led to? The cascade. So what it led to was far more important, the cascade. Common base itself was interesting in the sense that, for some application, low input resistance, maybe we looked at it, maybe very useful, so it's okay. But then it led to a cascade amplifier, which is a very, very popular configuration. In fact, many analog circuits that you pick up and you look at this schematic, you'll find a cascade there. Cascade or a folded cascade that I discussed today, you'll find it there. Differential pairs, you'll find it almost everywhere. Cascade, you'll find it everywhere. Common collector, you'll find. Common emitter, you'll find almost everywhere. And all right. So what I'll do is, I have a little bit of time. I think all of you are probably eager to know the question number 3 of the quiz, right? Okay. So let's look at it.